Life. Do you know what life is? It is cosmic dust, a random temporary phenomenon that has no significance on the vast stage of the universe. How often have you heard such disparaging remarks about what we call life? The most mysterious phenomenon in the universe. Black holes, magnetars, dark matter are not the most mysterious. We see traces of their existence all around us. Against the backdrop of the entire cosmos, it is life that seems to be some kind of anomaly. Yet manifestations of life have not been found anywhere beyond our planet. Life. What is it? In the midst of hundreds of billions of miles of empty rock and gas, something so strange emerges that it can stand in opposition to everything else. We are living beings, a part of the universe we see, and we are undeniably part of it. At the same time, the universe does not seem alive to us. Have you ever thought about the fundamental difference between living and non-living matter? And where does that line lie, where one ends and the other begins? From the point of view of ancient man, the differences were obvious. Non-living matter, for example, a massive rock in the dark, might very well resemble a living bear, but only living matter, only a living bear, could chase you in the forest, and no matter how hard you ran between the trees, it could catch you and tear you apart. Inanimate objects never do anything so purposeful. The giant boulder rolling down the hill is not really chasing you, the ancients reasoned. No wonder, since they'd never seen a homing weapon. Since ancient times, it has been believed that some animating factor is necessary to make one thing behave very differently from another. Aristotle, for example, believed that the essence of life was the ability to initiate motion without external influence. He thought that the same boulder rolling down the hill, once stopped, would never move again unless something or someone influenced it. On the other hand, living matter, like a sleeping bear, could be in a state of rest and then begin to move without any external influence. But Aristotle was wrong. Modern science easily recognizes the weakness of such generalizations. One could say that the bear also begins to move only because of external influences, such as a change in temperature. The change in temperature changes the chemistry of the processes in its body, and it wakes up. On the other hand, the nucleus of uranium, which we definitely don't consider to be alive, can remain unchanged for billions of years, and then suddenly and unexpectedly decay without any external influence. But Aristotle was absolutely right about one thing. He was right to call life a fundamental phenomenon of nature. You might say, in Aristotle's time, everyone believed that almost everything was made up of what we now call the Earth's biosphere. If the Earth's biosphere is at the center of everything you see and know throughout your life, you would naturally think that trees and animals are as important as rocks and stars. Yes, indeed, it was only after hundreds and hundreds of years of discoveries in astrophysics that it became clear that the universe is not only vast and completely indifferent to Earth, but is also governed by universal laws that do not even mention life. Charles Darwin explained the origins of the languages of life, which require no special knowledge. Even today, after discovering and studying numerous complicated life mechanisms, we have not found any special physics in them. After all this, it would be merely amusing to call life a fundamental phenomenon of nature. The concept of nature, in a broad sense, has become synonymous with the concept of physics. From the perspective of the modern layman, the distinctions between living and non-living matter are almost always obvious. At the macro level, we distinguish living from non-living at a glance. However, if we take any living creature and break it down into atoms, we would see that they are exactly the same atoms that make up stars and planets. The same atoms make up both what is alive and what is not. What is it that makes inanimate matter alive? No one has been able to find the magic quality that distinguishes living things from inanimate objects. For a long time after Aristotle, we continued to lack the fundamental true understanding of what living matter is. And now, modern biology is no longer waiting for something to give life to matter, because we have finally discovered the basis of life, the first step from which everything begins. Imagine a pile of stones being methodically thrown into the air over and over again. After each throw, there is a non-zero probability that the stones will settle on top of each other and form a particular structure. This structure will have properties that the pile of stones itself does not have. In other words, it will be something greater than the sum of its parts. This phenomenon is known as emergence. Emergence occurs when a complex entity has properties or behaviors that its parts do not have on their own, and only emerge when they interact into a larger whole. There are many examples of this phenomenon in nature. Of course, some configurations of atoms are less likely to exhibit certain properties, while others are more likely. You'll know what's meant in a couple minutes. By combining certain atoms in a particular order, we obtain a structure with properties that a simple pile of the same atoms lacks. This structure is called a molecule. Now we understand that the basis of life is not at the level of individual atoms. It is above that. The basis of life is molecular, and the characteristic of living molecules is that they cause the environment in which they exist to replicate itself. Some configurations of atoms actually tend to replicate, to make their copies with the help of the environment around them. These configurations are called genes. A gene is a property of atoms, just as fractal patterns, snowflakes, or ripples on a sand dune, or the giant geometrically regular hexagon on Saturn. The emergence of these emergent properties is certainly much more likely than the emergence of life. Nevertheless, all of the above are nothing more than systemic effects. In other words, atoms themselves are not alive, but once they are connected in a certain sequence, their emergent properties immediately manifest. This synergistic effect, where this configuration of atoms begins to order the surrounding environment in a certain way, creating similar configurations of atoms, is what we call emergence. There are many examples of emergence in nature. I could not possibly list even a small portion of them. So it is not surprising that no special physics has been found in living matter, because the emergent property of physics is chemistry, and the emergent property of chemistry is biology. Piece by piece, atoms come together to form molecules, which in turn give rise to whole organisms. The very magic that people have sought to find in living organisms is nothing more than the manifestation of the emergent properties of matter, where elementary micro-level processes, when combined, create incredibly complex macro-level manifestations. For the same reason, people who search for the center of consciousness in the brain have very little understanding of what they are actually dealing with. So one day, no one knows exactly when or where, matter on Earth exhibited extremely rare and highly improbable properties. Under uniquely favorable conditions, the first replicator spontaneously emerged from a cluster of atoms. Upon its appearance, it began to reproduce. That was it. With uncontrolled replication under limited resources, we get competition. The self-copying of the replicators is not perfect, leading to mutations. Mutations produce variations of genes, which produce variations of species. Competition plus species variation equals natural selection. Natural selection plus time equals evolution. Yes, all life on the planet is based on replicator molecules we call genes. Therefore, there is no division in the universe between living and non-living matter. Matter is the same, and life is simply its emergent property. But does this answer the question of what life is? Don't get ahead of yourself. A gene is the smallest indivisible unit of hereditary material that can be passed from parent to offspring. Genes determine the makeup of the entire organism, its functions, traits, and characteristics. Genes are the instructions that build the whole organism. Modern science tells us that what an organism will be like is determined by genes, but only half of it. The other half is determined by the environment. I find this formulation very annoying because it gives a poor understanding and diminishes the true significance of genes. Roughly speaking, it's as if tomato seeds could grow into red cactuses if planted in the desert. From my point of view, a better formulation would be: genes imply a certain variability of the characteristics of an organism depending on the conditions of the environment. Thus, a gene can be a replicator only in a particular habitat or niche. The niche is the environment in which an organism can survive and reproduce. And what is characteristic, from this point of view, is that the organism itself becomes a niche for genes. You may not fully grasp the essence now, but you will soon. Richard Dawkins, who for some reason is known as the planet's leading atheist, actually has much more impressive accomplishments and did not initially become popular because of them. In 1976, Dawkins published the book, The Selfish Gene, in which he significantly deepened the theory of evolution. Unlike Darwin, who believed that the fittest variant of a species survives, Dawkins proves that it is actually the fittest variant of the gene that survives. Thus, all evolution ensures the well-being of those genes that are most effectively replicated. Yes, the unit of evolution is the gene, not the organism, as many believe. For example, the genes responsible for a huge peacock tail clearly do not simplify the life of an individual peacock or the entire peacock species. But these genes prove to be the most successful compared to their direct competitors. The main characteristic of a replicator is that it always causes its own replication. It forces the environment to replicate it. Thus, biology is primarily the science of studying the influence of genes on other matter. What is a bear? It is a giant container of genes. Take, for example, the insulin gene. It cannot replicate itself. It is critically dependent on the presence of all the other genes in the bear's body. But that's not all. It also needs genes from other organisms in the external environment. A bear cannot survive without food, and the genes for producing that food can only be found in other organisms. Therefore, genes collectively construct the bear's body, forcing it to do many different things, including hunting, so that the genes can replicate themselves. The bear's body is the immediate environment manipulated by the genes for their own replication. You see, they are creating the bear and programming its behavior, making the animal follow algorithms that are designed not to copy the bear, but to copy the genes present in its body, and they do it at all costs. Note again that the bear itself is not a replicator. During reproduction, the bear is not copied. The new bear is recreated according to the blueprints encoded in the DNA of the parent organisms. The organism itself is not a replicator. It is a part of the replicator's environment, usually the most important part after all the other genes. The rest of the environment is the type of habitat the organism can occupy, such as the top of a mountain or the bottom of the ocean. And the lifestyle within it, such as being a hunter or a filter feeder, allows the organism to survive there long enough for its genes to replicate. So the organism is the immediate environment that copies the actual replicators, the genes of that organism. Previously, for example, the bear's nose and its cave would have been classified as living and non-living objects. But at the core of this division, there is no fundamental difference. The role of a bear's nose is not fundamentally different from the role of its den. Neither the nose nor the cave is a replicator, although new examples of both are constantly appearing. Both the nose and the den are just parts of the environment that are manipulated by the bear's genes during their replication process. Genes that need to work together to replicate are linked together in long chains of DNA. Different organisms, such as microbes, plants, or animals, are constructed from these chains, and we consider these organisms to be living. Such an understanding of life, in which organisms are considered in relation to genes as part of a surrounding environment, has been present in the foundations of biology since Darwin's time, but it was almost unnoticed until the appearance of Richard Dawkins' works, The Selfish Gene in 1967 and The Extended Phenotype in 1982. Living molecules are just molecules that obey the same laws of physics and chemistry as non-living molecules. They contain no special substance and have no special physical properties. They simply become replicators in certain environments. More precisely, a gene can be a replicator only in a very limited number of environments, while it will not be a replicator in a vast number of other environments. So, why did I suddenly decide that life is a fundamental phenomenon of nature? Why is it worthy of this status? After all, its influence seems negligibly small. We do not know if there is life beyond Earth. By the way, I recently made a video about why we cannot find extraterrestrial life. I recommend watching it if you haven't already. But even if life is widespread, its manifestations seem too insignificant to be detectable. When we look up at the sky, we see an active universe filled with various powerful but completely non-living processes. Galaxies rotate, stars ignite, burn, explode, and collapse. High-energy particles, electromagnetic waves, and gravitational waves propagate in all directions, and it seems irrelevant whether life exists among all these titanic processes, since it is unlikely to affect even one of them. If a massive solar flare were to engulf the Earth, an event that is insignificant from the point of view of astrophysics, our biosphere would immediately become sterile. But on the Sun, this catastrophe would have the same effect as a raindrop on the eruption of a volcano. Our biosphere is a negligible part of the mass and energy of the Earth, let alone the Sun. The solar system is primarily composed of the Sun, whose mass is 740 times greater than the mass of all the local planets combined. Yes, the solar system is primarily the Sun. Well, and to some extent Jupiter. With such a calculation, everything else in the solar system, except the Sun and Jupiter, can be considered insignificant impurities. Moreover, the entire solar system is a tiny part of the Milky Way, and the Milky Way itself is an unremarkable galaxy among many others in the known universe. Stephen Hawking once said, "The human race is just a chemical scum on a moderate-sized planet, orbiting around a very average star in the outer suburb of one among 100 billion galaxies." I probably don't know anyone who would disagree with that, but it is not true. Now I will try to explain why this view is the most profound misconception of modern times. Ask yourself this question. The basis of life is the gene. What is a gene? It is a piece of hereditary information. Bears, humans, flowers, bacteria, everything we call life is just a way for genes to copy themselves. The more accurate information about the environment a gene contains, the more successful it is in reproducing, because with reliable information about the environment, the gene can live and reproduce in that same environment. Genes with more accurate information about the world outcompete genes with less accurate information. The vast majority of genes with incorrect or less accurate information about the environment could not survive or reproduce in it long enough. Survival of the fittest, right? But what is environmental adaptation? Adaptation to the environment is having accurate knowledge, objective information about that environment. It's not that genes can know anything, but evolution is when, through trial and error, genes are selected that have more complete and reliable information. The human eye is not perfect. We are far from understanding how far it is from seeing the universe as it is. However, it has proven to be good enough for humans to perceive the world with some degree of accuracy. And of course, through a combination of factors, it has made us the most efficient species on the planet. This is because the genes responsible for the formation of the human eye carry enough accurate information about the surrounding world to allow the entire organism to perceive that world adequately. This is true of all living things. Genes exercise highly precise interactive control over the reactions of a complex environment, the organism, to everything that can happen to it. And this control is aimed at eliciting a specific response to the effects of the environment on the genes, namely replication. The more external situations the genes can survive without perishing, the more successful they are. In this context, the human brain is potentially the best that genes have managed to build. The more information in the genes corresponds to the environmental conditions, the more copies these genes will leave behind. So you can say that evolution is essentially a kind of computation, and genes are literally embodied information about the environment. Notice this. All the sensations you experience throughout your life, the colors and geometry you see, the sounds you hear, the hardness or softness of the ground under your feet that you feel, your ability to move in space, your ability to feel that water is wet, mud is sticky. Ultimately, you have manipulators in the form of hands. All this did not come out of thin air, but from the fact that genes have evolved over millions of years to carry the most reliable knowledge about the environment. And that knowledge is embodied in you. It is precisely because of this embodied knowledge of the world that you are capable of interacting with the environment, receiving stimuli, and manifesting a responsive response. And vice versa, you are also capable of giving stimuli to the environment and receiving a responsive response from it. Due to the absence of certain genes, such as those that allow us to see the full spectrum of electromagnetic waves, it is possible that some things in the universe are fundamentally unknowable to us, and perhaps this is for the better. But we have genes that give us a predisposition for unprecedented abstract thinking, which allows us to learn about certain phenomena that are beyond our sensory level. In other words, genes carry knowledge about their niche. Everything that is fundamental to the phenomenon of life is determined precisely by this property, not just replication itself. The primary aspect is the presence of accurate knowledge, because genes with unreliable knowledge are not viable and die out quickly. Genes that reproduce the environment less accurately always lose to genes that reproduce it more accurately. In such cases, we speak of better adaptation of genes to their niches. Why is the presence of accurate knowledge primary and not reproduction? Because we can imagine a species of genes that may not be able to replicate, but are adapted to maintain their form against external influences, for example, able to withstand corrosion and other forms of destruction. Such a species would be unlikely to arise naturally, but it could be created artificially. Once the production of these artificial organisms stops, the number of examples of each gene cannot increase, but it will not decrease either. As long as the knowledge contained in these genes is sufficient to carry out the survival strategy of these genes, they will occupy their niches. And here we can see that the survival of valid knowledge is fundamental, not necessarily a gene or any other physical object. So strictly speaking, it is a piece of knowledge that adapts to the niche, not a physical object. If the adaptation is successful, that knowledge acquires a property. Once embodied in that niche, the knowledge will strive to remain there. The gene in the form of its physical shell is not so crucial because, on the one hand, in the case of the replicator that implements it, its physical material is constantly changing. A new copy is assembled from components at each replication. On the other hand, non-replicant knowledge can also be successfully embodied in different physical forms, as when old records are transferred from vinyl to magnetic tape, then to compact discs, and so on. Finally, humans may one day copy the knowledge contained in their genes onto the most reliable medium available to them in the future, replacing all their fragile biological components with something more robust. It would be strange to call these future beings inanimate. For example, if you do not believe that the body is a special vessel for the soul, but still claim that artificial intelligence is impossible, that is literally the same as saying that the brain is not a physical object. But the terminology is not important here. The point is that although all known life is based on replicators, in reality it revolves around a single phenomenon, knowledge. What is life then? Life is the physically embodied knowledge of a niche that compels its niche to maintain the existence of that knowledge. I fully understand that this may sound like a bunch of crazy words and nonsense if you haven't really grasped what I've been talking about, but perhaps this is the deepest definition of life that we can provide, summarizing all that has been said. However, any skeptic would stop me and say that knowledge is a human concept. In other words, knowledge is something important to us humans because our ecological niche depends on the creation and application of knowledge. Outside of humans, this concept has no meaning and is irrelevant to the rest of the universe. But the skeptic is critically mistaken. Knowledge is not only important for Homo sapiens and not only on planet Earth. Let's consider the astrophysical consequences of knowledge. As of today, we have a cool theory of stellar evolution that describes the structure and development of stars. However, about 100 years ago, we didn't even know the source of solar energy. The best physics of that time only provided a false conclusion that, regardless of the source of its energy, the sun couldn't shine for more than 100 million years. Then nuclear physics was discovered and applied to the physics of stars with all its intricacies. Now we understand why stars shine. For most stars, we can determine their temperature, the color of their light, and diameter at each stage of their existence. Learn the duration of each of these stages, identify which elements the star creates through nuclear reactions, and so on and so forth. This theory has been repeatedly tested and supported by observations of the sun and thousands of other stars. We can use this theory to predict the future development of the sun. It tells us that the sun will continue to shine with great stability for approximately another 5 billion years. Then it will expand 100 times and become a red giant. Subsequently, the outer shell of the sun will disperse into space, forming what is called a planetary nebula, and the exposed core will gradually become a white dwarf. After tens of billions of years, the white dwarf will cool down to the point where it will no longer emit visible radiation, becoming a black dwarf. But will all this actually happen with the sun? Is every star composed of the same mass that formed 5 billion years before the sun? Has it already become a red giant, as the theory predicts? And is it possible that some seemingly insignificant chemical processes on tiny planets orbiting these stars could alter the course of such global processes? Is it conceivable that a cluster of chemical dirt could influence unimaginably large nuclear and gravitational processes operated by immeasurably larger masses and energies? If the sun does indeed become a red giant, it will engulf and destroy the Earth. If, by that time, our descendants still exist on Earth, they most likely would not want that to happen. They would do everything in their power to prevent it. Are we 100% certain that they won't be able to do anything? Of course, our current technology is too weak to tackle such a task. But that doesn't mean the problem won't be solved in the future. In fact, we already have a rough idea of what it will take to solve it. Specifically, the removal of matter from the sun. And we still have a whopping 5 billion years to perfect our plans and put them into practice. Now pay attention. If our descendants save themselves using this method, it means that our current theory of stellar evolution, applied to one specific star, the Sun, gives completely the wrong answer. The reason is that it does not take into account a fundamental parameter. It takes into account fundamental physical effects related to nuclear and electromagnetic forces, gravity, hydrostatic pressure, but not life. It does not take into account the influence of life on stellar evolution. You see, it's impossible to predict the future of the Sun without considering the future of life on Earth, and especially the future of knowledge. The light from the Sun in 10 billion years will depend on gravity and the radiation pressure from convection and nucleosynthesis. It doesn't depend at all on the geology of Venus, the chemistry of Jupiter, or the pattern of craters on the Moon. But it does depend on what happens to life on planet Earth. It depends on politics, economics, and the outcome of wars. It depends on what people do, what decisions they make, what problems they address, what values they cultivate, and how they behave in general. Such a theory does not follow from the laws of physics or any other fundamental principles we know. It can only be proven in a high-level human language. Therefore, astrophysical predictions require theories about the activity of life. Even if you are a skeptic and a pessimist and don't believe that life on Earth will last that long, you still can't escape the same conclusion. For even if the human race's attempts to survive ultimately prove futile, space is vast. If some intelligent life in some galaxy ever manages to survive for billions of years, it means that life is inevitably essential to the overall physical evolution of the universe. Therefore, in our galaxy, and in any other stellar evolution, depends on whether intelligent life has evolved, and when and where it has evolved. Yes, we don't have any reliable confirmation of extraterrestrial life, let alone intelligent extraterrestrial life. So far, in the universe as we observe it, life hasn't affected anything that would have any astrophysical significance. But as you know, the speed of light is extremely slow on the scales of the universe. When we look at the sky, we see the past, and the farther we look into the universe, the farther back into the past we look, and the less detail we see. As our theories about the structure of the Milky Way become more refined, we will be able to make more accurate predictions, but again, only based on assumptions about the distribution and behavior of intelligent life in the galaxy. If these assumptions are not correct, the error in the prediction will be almost as inevitable and crude as if we were wrong about the composition of interstellar gas or the mass of a hydrogen atom. Cosmologists John Barrow and Frank Tipler considered the astrophysical manifestations that life would have if it lasted long enough. They discovered that life would eventually cause major changes in the structure of galaxies and eventually the entire universe. Moreover, it is quite capable of gaining dominance over everything that happens, just as it currently dominates the biosphere of Earth. Any theory of the structure of the universe in all but the earliest stages must take into account what life will or will not do by that time. This cannot be avoided. We cannot ignore the fact that the future of the universe depends on the future history of knowledge. We are accustomed to justifying the insignificance of life by attaching too much importance to general quantities, such as size, mass, and energy. From the perspective of modern science, these are indeed good measures of significance. But in the context of biological processes, they are poorly applicable. Therefore, there is no reason in physics why they should remain so. The biosphere itself provides many counterexamples. For example, in the 3rd century BC, the total mass of the human race was only about 10 million tons. One might conclude that the presence of such a small biological mass could not cause physical processes that would result in the movement of masses many times larger. However, during the same period, the Great Wall of China was built with a mass of 300 million tons, which is 30 times larger. Today, it takes only a few dozen people to dig a railroad tunnel, moving millions of tons of earth. These thoughts become even more pronounced if we fairly compare the mass of the stone moved with the mass of that tiny part of the brain of an engineer or an emperor, where the ideas that led to the execution of that work are embodied. 100 years ago, we heated our stoves with firewood. Now the human race may have enough knowledge to destroy entire planets if its survival depended on it. Even irrational life has significantly changed the substance of the Earth's surface and atmosphere, which in mass far exceeds all the oxygen in our atmosphere. About 1,000 trillion tons of oxygen have been produced by plants. It has become a byproduct of gene replication, the offspring of a single molecule. Life exerts influence not because it is characterized by greater masses or energies than other physical processes, but because it possesses more knowledge. In terms of the macroscopic effect that knowledge has on the outcomes of physical processes, it is as important as any other fundamental physical property. But there's something else. In the previous video, we concluded that we most likely all live in a multiverse. Let's compare a living lion and the constellation of Leo. Living lions in many nearby universes are anatomically very similar. This is true not only of their genes, but of their entire bodies. In the Leo constellation, however, there is no such regularity from one universe to another. The shape of the constellation is strongly influenced by chaos and depends entirely on the initial state of the galactic gas from which the stars were formed. This state was random on a microscopic scale, highly random in different universes. The process of star formation from this gas involved various instabilities that increased the scale of variation. As a result, the arrangement of stars that we observe in this constellation exists only in a very limited range of universes. In most close variants of our universe, there are constellations in the sky, but they look completely different. In a particular universe, the most prominent structures are galaxies and galaxy clusters. But in the multiverse, these objects have no discernible structure. In the multiverse, where one universe has a galaxy, there are countless galaxies with highly variable geography. Nearby universes resemble each other only in certain general features, as required by the laws of physics that govern them all. Yes, most stars in all multiverses are fairly spherical, and most galaxies are spiral, but nothing extends far into other universes without unrecognizable changes in the details of its structure, except in those few places where knowledge is embodied. In these places, objects extend over a large number of universes while remaining recognizable. Genes with the best adaptation will have the same structure across a wide range of universes. If only the entire multiverse could be observed through a telescope, life and its consequences would be immediately apparent. Places touched by life in the universe differ from other places, just as cultivated fields differ from wild jungles on satellite images, just as crystals differ from the solution in which they grew. And despite the seeming insignificance of life, it is precisely what gives rise to the most large-scale, regular, and diverse structures in the multiverse. Thank you for watching.